Okay, question 2 here. Let phi from G to H be a homomorphism. Prove that the kernel is a normal subgroup. Sure, so of course remember that the kernel is the set of things in G which end up getting turned into the identity in H. So prove that it's a normal subgroup. So just like the previous question, proving something is a normal subgroup, you got to prove it's a subgroup, and you got to prove that it's normal. But again, much like the previous question, I think proving that it's a subgroup is you've been doing that for a while, so we can kind of skip over that, and I didn't really worry about that part. But here it is as a summary, or kind of the whole thing really. Why has it got to be a subgroup? Okay, well, it's got to be closed first of all, because if x and y are in the kernel, then that means when you do this to them, you get E in H, right? So then, of course, that means the product, since phi is a homomorphism, and I know I realized I'm mixing my capital and lowercase phi's here, but that's okay. That's going to be E as well, because it's just E times E. So that means I wish there was an undo button. So that means that's in the kernel. So it's closed under multiplication. Okay? Now, of course, the identity gets mapped to the identity. That's a thing you for sure know about homomorphisms. And inverses of stuff, if x is in the kernel, so that phi of x equals E, well then x inverse is surely in the kernel, because phi of x inverse is phi of x inverse, which is E inverse, which is E. So again, this part's kind of boring, not really important. Whatever. So the point is, it's a subgroup, right? And everybody probably believes me. So the hard part is, what about the normal subgroup? So again, you got to say pick something in the kernel and consider anything in G. And what we want to know is this in the kernel. By the way, I should have mentioned this maybe on number 1. Some people conjugate it the other way around, like they do. Geez, dude. Like they do G inverse XG. That's fine. It's whatever. It's left hand, right hand stuff. Like they're different, but equivalent ultimately. So it's whatever. Okay. So anyway, so we want to find out, is that in the kernel? So we want to know what happens when you do phi to it. Well, let's find out. Well, for one thing, because phi is a homomorphism, I know I can do this. This is just phi of G, phi of X, phi of G inverse. And then what can I do with that? Well, I can't really do anything with phi of G, because G was anything, right? G could, I don't know what G's deal is. X, though, I know is in the kernel, so I know phi of X is E. Why did I just write that again then? Phi of X is E. And of course I mean E in H, so you can write that for clarity if you like, or you can omit it. Everybody probably knows what you mean. And then finally, phi of G inverse, I don't really know much about that, but I do know that it is whatever phi of G was, it's the inverse of that, right? And that's super useful because that EH in the middle, of course, that's just like times 1 or plus 0 or whatever. It doesn't do anything. So this is really phi of G times phi of G inverse. And so, boom, that is the identity. In other words, we can see that phi of Gx G inverse gets mapped to the identity. In other words, Gx G inverse is in the kernel. And now, X was anything in the kernel, and G was anything in G. So it turns out that the kernel is closed under conjugation. And in other words, what we were calling um, option 1 here, definition 1 of being a normal subgroup. So yes, the kernel is a normal subgroup of G. In fact, notice that notice actually, and this is kind of an important point, that when we were talking about this, I didn't really mention H at all, except saying, it gets mapped to the identity in H. But like, what the deal is with H, what the structure is over there, how big is it, what are the other elements, how are they all related to each other, it does not matter at all. H is totally not relevant. The point is that that the stuff in G is going somewhere, and the stuff that gets deleted when it goes there is a normal subgroup of G. And where is it going? Who cares? That's not really the important. And so I don't know. Thinking of it that way, I think is a useful way to think about it, especially for the next problem. But that's it for this problem. We will call it there.